Okay, it's always such a joy to hear back from our viewers and to give them what they want. We saw you loved our deep analysis and breakdowns of the rash of humanoid bot hands that we've been seeing in the past few weeks. We heard you wanted a breakdown of the Wuji tech humanoid bot hand from China. And so here we are to break it down for you. Ladies and gentlemen, I present to you the Over the Horizon expert panel, Scott Walter and Gustav Andersson. Scott is a mechanical and aerospace engineer and two-time founder of robotics companies. Gustav is a hand surgeon and associate professor of anatomy in northern Sweden. Welcome, gentlemen. Great to have you back on.
Welcome, Rock. Welcome, Scissors.
Always a pleasure, Paper.
So, when we last spoke about the Chinese robot games, we were all wondering about the hands. Where are the hands? And in the past few weeks, there's been a rash of bot hands that have come out from China, haven't they? Let's take a look at Wuji. This is the latest. Scott, if you can just run us through what we're seeing, and then we go and do.
Oh, yeah, we're seeing quite a bit there. And of course, Gustav is going to do a breakdown of a lot of those gestures and the capabilities of the hand. But unlike some of the others, we get a really good detail of what's going on underneath the skin. So there's no room for doubt on how they're doing this. And that's what we're going to go into a really deep breakdown of that. And I'm actually surprised that they've revealed as much as they have. There's a few little things I'm not quite sure about, but I think I have some reasonable guesses on how they are doing all the articulation. And if it's not obvious at this point, they're not using tendons.
Yeah, they're doing like the what do you call it? The anti-version of Elon's approach of moving it all to the forearm, and they're saying, damn it, we'll keep it in the hand. So there's no compromise.
Yeah. And you can see it's rather remarkable how it's able to move. We've taken a bunch of screenshots, so we can't go into detail and everything right now without stopping the video all the time. So the plan is to kind of go through some of the rather interesting screenshots and break down what's going on. And again, look at operations like this and decide, okay, is that really hard for a humanoid hand to do or not? You know, should we be impressed by that or not? Should we be impressed by the scissors demo? That's definitely for Gustav. He talks about scissors. I talk about paper. And, you know, other kind of grasping and different gesture operations that are going on there. So that's the plan we're going to do. So I think everyone's going to want to buckle up and get an idea of what's going on. But the first question I'm going to pose to both of you gentlemen is the name of the company, Wuji Tech. What does Wuji mean?
My Chinese is limited, but isn't the Wu something with Marshall? At least one of the...
It could be. I think it literally means like limitless or infinite. But I think it's also part of a lot of philosophy and Taoism and everything else. So it has other meanings of like emptiness and everything else and being a circle. So I'm sure it has like a dozen meanings. And I just thought, is it just a name? And it's like, well, why not find out what it means? And I think they're probably looking at it as like, you know, the infinite possibilities that are here. Now, the one thing I must say about this is that not only is it robust, but I think the one thing we should learn here is that you don't want to take a blow to the jaw from that thing. That's going to break bones.
For sure.
Like that. So it's extremely robust. And then we're seeing some other operations here that because of the way it's actuated, this does not surprise me at all. It should be a very repeatable, be able to do that. And we will discuss that a little bit more in detail.
So this is the view with the glove horn.
Yes. Yes.
And I'm not sure, and I'm going to ask you this later to break it down for us. I don't see any sensors.
There doesn't seem to be any sensors right now. There are encoders, but I'm not aware that there are any sensors in there. You can get some information from it, but you know, that's probably something they'll be getting to. You know, for the first version of a hand, it's not too bad. But then again, we don't know about the glove because the glove seems to be pretty thick. They could be doing a lot of other things in there. They could be adding a lot of sensors and just not talking about it right now. So it may be that the baseline is like, this is what the actuation is going to look like. And when we get to the sensors, we'll do something else, which might make more sense because routing of cabling and everything is just so tricky through all these motors that you might almost want to have an outer scan that has everything built into it that will simplify that.
But they must be getting some feedback from the actuators, I guess, about positioning and force.
There's a slide about that. So
why don't you bring up your deck?
Yeah, I'll go ahead and bring that up. And one of the first things that everyone probably wants to know is like, where did this company come from? And my understanding is they actually are a company that makes motors, and they do these exquisite windings. They seem to be much tighter winding coils than a lot of other companies, which means they're probably in a better position to miniaturize. And so we should not be surprised that they were then able to take this and figure out, hey, how can we use this tech to make it a little bit better? Now, I think I am sharing, am I? All right, there we go. That looks a little bit better. So again, that's one of the first images that come in here. It's the Wuji hand. I assume that's how it's pronounced. And I just grabbed this screen not to necessarily talk about the spinning of the pen, because it didn't really spin the pen, but just give an idea what the proportions look like. So it does kind of resemble a human hand reasonably well with the glove on there, rather remarkably. And we see a couple other images of some of the gestures that'll be possible. This is basically in order of how it went through, and we'll pick this up a little bit later. But what I'm more interested in is, of course, the actual skeleton that's going on and how all the actuation is being done. So first they bring us through some specs. It's fairly light overall. So it's under 600 grams, which means it's probably about 1.5 pounds, something like that. So it's probably, reasonable mass for a hand design, especially when you consider that's all of it. There's no forearm mass, nothing. That's the whole thing, everything that you need right there. Now, they say it's super dexterous because there's no coupled joints, and that makes sense, which means they can actually do gestures that we probably can't do as humans because they have individual control of every single IP joint. So, yeah, it's going to be super dexterous with remarkable control because none of the joints are coupled and they are all fully actuated. And the big question is like,
hand had coupled. That's what the passive meant, right? They had 5 passive joints. And that would be
exactly.
like a coupled joint of the distal.
Yes, exactly. Right? Which is exactly what happens. You're pulling that puppet string and like everything moves, and it's really hard to straighten it out with without your intrinsics and all that other stuff that we've talked about in the past. So this is going to have better capabilities than just about any tendon-based hand, unless you have more than 16 action. I mean, even all of them are not necessarily directly trying to move one IP joint. They're trying to move the whole finger, and then with antagonism try to get certain gestures. This is like going directly to the joints. So I think it's a pretty interesting actuation strategy as a result. Okay, so now as far as payload, I mean, there have been some other hands out there that have also tried to go to using microdrives, and their payload capacity has not really been that impressive. So here we have a fingertip force of 15 newtons. Most people may not be familiar with newtons. It's just kilograms times gravity. Gravity is approximately 10. Divide by that, that's 1.5 kilograms of a weight that would be able to hold, if you want to think about it that way. Technically, it's mass, and which means it's a little bit more than 3 pounds, something like that, maybe 3, not quite 4 pounds. But the static grip load, so that's like an individual finger, but the overall static grip means it can pick up something. And I think they showed somewhere in the video of it picking up a big, heavy jug of water that would be about 20 kilograms. So that's pretty reasonable. That's a little bit more than a carry-on bag as far as being able to hold that for grip strength.
How does it compare to a human hand then in the tip force?
Well, it depends upon the human, but I think a lot of us, we're able to lift up weights that are like 50 pounds or more. Okay, so this is not quite 50 pounds. That would be like 23 pounds. You think a checked luggage is right around 23 kilograms. And so that means most people can pick it up. We obviously can go way more than that. It would be nice, but this is pretty impressive for a hand that is using direct drives like this. It definitely is. Now, they refer to it as being true to human anatomy. That can be up for discussion. I basically think it's truer to human anatomy than others, and we'll kind of get into that a little bit. I mean, part of it is that the palm line looks pretty good, especially when it's clenched. It looked much better than everyone else. And I think you've brought that up a lot, Gustav, about how that angle is a little bit wrong. They seem to be a bit more inspired, but I will point out some of the things they get a little bit wrong.
So they have the curvature of the MP joints being shorter and shorter.
Yeah,
but they seem to be going for a 1 finger length design. So each finger is the same size for obvious reasons easier to produce, I guess. But
Yeah.
I would like it to be a smaller little finger, which we can see in
Yeah,
some
I
of the grips.
noticed.
But it's
But
obviously
the line is pretty good, because you'll notice when they do this, that line, and we'll see an image of that later on, that it is. So that's why I kind of threw in the editorial comment there that's more truer, but at least like the overall dimension, it's not like oversized from a human hand or undersized. It's about the same size. I think that's pretty much what they mean by 1-to-1. Okay. So now here are a couple other images that we'll get back to give us an idea of what the overall mechanics looks like from different angles. And these images here kind of give us some hints on what's going on. And I'm going to try breaking these things down, because we really want to understand what's going on in the different knuckles, especially up by the palm, and how the thumb and everything works. And the curiosity is like, how are they actually actuating all this thing? So,
and it's interesting that the knuckles are not all at the same level.
Yeah, well, that's part of to get the arch a little bit. It means your fingertips out there, and Tesla and others have done something like that. So they should be offset. And I think they are kind of offset fairly true to human anatomy. Where they're failing is in their length. So the pinky looks a little bit shorter because it's offset. The reality is it's not as short as
it should be.
It needs to be. It needs to be a little bit shorter. Yeah. Okay. And, they talk about this thing having superior grasp. I left this thing here. This is a nice image because it gives you an idea of how much thickness the glove kind of adds to it. So the skeletal bones that are in there are actually quite thin. But then when you put that on there, it starts to resemble a bit more of a human hand without being, let's say, too fat. But at the same time, it looks like they'll probably have some decent cushioning going on in there. So yeah, when we look at it, it looks pretty realistic. The only problem is they probably had to find the special glove manufacturer to actually make the finger links all the same. When I go out there and buy gloves, usually the pinky is a little bit shorter. Yeah. So, but they have a nice soft outer envelope that results in interesting things. All right. Now, before we get in too deep, there's two things we want to do. First, we will be doing some comparison to the Tesla bot hand, since that's a good reference point. But the main thing is the terminology that Gustav and I are going to be throwing around all these terms like, phalanges and IP joints and everything like that. So everyone may want to just freeze the screen, go back to the presentation, freeze the video right there, and go through, if you're not familiar with what's out there, so you can see that our digits or our fingers are made up of phalanges, which are the little pieces of bone that make them up, and we give them names like the proximal, the one that's closest to the palm. The one in the middle is called the middle. I don't know why they didn't use a Latin term. And the one at the tips at the very end are usually called distal, and the joints between them are usually called dip, pip, and MCP. So the dip is the distal interphalangeal, and then we have the proximal interphalangeal, et cetera. So we're going to be using those terms as we go through. I just want to make sure everyone's familiar. And when we talked about flexion and extension, it's basically when you're clenching, and when you're splaying out like this, that's when we're talking about add or abduction. Okay, so now that we get that down, we can kind of proceed ahead here and start asking the question, okay, how is this being actuated? How are the tips moving? And the first thing I want everyone to do at home is like look at this and identify where is the pip and the dip joints on here. So look at that. Okay, time's up. Here we go. Okay, so I'm identifying where the dip and the pip joints are, and you can see where all the axes of rotation are along here. So that means something is magically making these things rotate around there. And that's what we want to figure out is what's going on. You might imagine that, did they put like a teeny tiny motor in that axis in there? And that would be one approach, because that's exactly the approach that most robots do for like the elbow and the knee and everything else. The humanoids is that you put a big motor right there, and the axle of the motor also forms the hinge of that joint. So that's one possible approach, but it would be really small. Yeah, it would be really small. And I think there are a few that have done something like that, and they're just too weak. Yeah. So you just can't do it that way. Okay. So then as we kind of move on down here, we can also see that we have these other fingers here as we get on down here to not the pip and the dip, but what's the MCP joint. So this is the knuckle at the base. And the difference between this and the others is that this is one axis of rotation, purely one axis of rotation. So for reference, we're kind of moving on down to take a look. And yeah, actually, before I kind of give away the answer. The first thing is, can you identify the abduction axis and the flexion axis of the MCP joint? And I think it's pretty obvious. We should be able to see these over here. These kind of brass colored things with on there actually form the rotational axes for abduction. Or sorry, yeah, that's the abduction. But you'll see there's one below it that is actually for the flexion. So we can see these horizontal red ones here are the flexion. That is actually where the abduction happens.
Wow.
And then finally, we can look at the two together. Now, that's a bit unusual because the order of operation is different than everyone else does. Usually, the flexion axes are all serial. And, you know, the abduction comes first, and then you have flexion, flexion, flexion. But here we have flexion, abduction, flexion, flexion. And that's a kind of a mechanical design. And we can compare this. I think I brought up that, yeah, if we look here at what Tesla did, we can see that the abduction comes first, these little arrows down at the bottom here. And then you'll see the green lines up here are showing then the other two flexions that are along there. And that's common with many of the others that we've seen. And this also results in the finger movement not being quite as natural because that flexion is too high. Ideally, in the human finger, they are at the same joint. They're right there. They're not. There's not that offset. And that's sometimes results in their clenching being a little bit off. And this is why when they say it's, you know, the same as a human hand, it's like, it's not. Unless that's a ball and socket joint there, it's not. But in order to pull this trick off, everyone usually has to have that little offset of one joint down below the other. I think the only one where I see an exception is that the Neos hand for Neo from 1X. Seems like they actually have the two right there. And it really is anatomically correct at that point. So that's a little difference. But now we're going to understand why it ended up that way, because we have to start identifying how did they go ahead and actuate these things in the first place. Okay. Yeah.
So immediately, I have one question for you, Scott, and which is when I compare this with the Tesla bot hand, the fact that you've got the abduction and adduction a little higher up in the joint. I'm wondering about the robustness of that, because if you have stress, is it better to place it there or a bit lower at the knuckle, traditionally, like the human hand?
That's a good question, but for the tendon-based hands, it may be a little bit different to get the kind of strength that you want. But because of the actuation strategy they have, it may not matter. It's just going to be the robustness of the joint itself. And they can make these things pretty mechanically robust if they want to.
I mean, if you put it further out, the lever arm would be smaller, right? So any stress on the tip of the finger would not be as big as if you put it higher up. Or am I thinking incorrectly there?
That's
a little bit. It's And you'll see that they actually are pretty close, even though the abduction is above the flexion. It's just a little bit above. It's almost identical to that location.
But the actual motor for both of these would have to be in the phalanx, right? In the proximal.
Yeah. I'm getting to that. We're trying to figure out how it does all these things. So the first thing I'm going to do is I'm going to identify the different features on the hand. So if we look here, in yellow is the distal phalange. And these things are basically inert. There are no motors. There's absolutely nothing in there. They're just chunks of metal that have about the right size and shape. And if you look at them very closely, you'll see on the back sides, there appears to be what looks like fingernails that they put on there. Now, even though there's a glove that's going over it, there does seem to be something, and it'll be more obvious when we look at the thumb a little bit later. But right now, that's where the distal phalange is. And you notice for the fingers themselves, there is nothing. There is no electronics or motor in there. When we get down to the thumb,
and I'll come to that later.
Yeah. And then on the thumb, it's the opposite. Actually, the phalange, as we're going to see, does have an actuator built into it. So the difference here is that these are inert, and the actuation is actually being done from the phalange underneath it. So the distal tips are actuated by actuators in the medial phalange. And that's basically how it happens, is that they're all being actuated by the one below. Okay. Right here in blue is what I'm calling the IP reducer. What this means is that this is some kind of gearbox, which is taking the rotation of the motor, which we're going to see here in a second. So this is where I'm saying are the phalangeal motors. So these little motor segments are coming in here and they're building up each phalange. And then there's like a joint at the bottom of each of those motors, which is also kind of an inert piece that just forms a connection between that and the reducer below it. And then finally, we just have what I'm calling like the motor interconnect, because your proximal phalange is longer than the others. And it actually has two motor sections in there and something together that makes it very long. But then when you go up the tree, you want to reduce the length of it, so you can't put two motors in the medial. And the only question is that, whether that motor interconnect always has to be the same size because it looks that way. Because if they could make it a little bit smaller, they might be able to shorten it. But at the same time, they have to be cognizant of the idea of the Fibonacci sequence series of being able to make sure everything rotates around. And I haven't gone and measured the distances here to see if they're respecting that. I'm assuming they are, but it could be that just because the way things turned out, they didn't get it because mechanically they were thinking about how do we build this mechanically versus it. Okay, so if we just go,
that's a very interesting point. I just want to pause there for a moment. Explain the importance of the Fibonacci sequence for the biomechanics of the body.
Gustav, that's your bailiwick right there.
Well,
go for it, Doc.
Yeah. So basically, it's for the fingers to be able to curl up to reach the pad towards the hand. At least that's how it turned out in us. If we don't have the Fibonacci sequence, when you do the full flexion of the fingers, the distal phalanx would be too long and kind of strike in here, or at least you would not have a tight fit. This one would be too long and that one would be too long, so you would have like an empty hole in there. So I think that's kind of the result of it being the Fibonacci sequence. Whether or not it was the driving function or not, that's the hen and the egg, but that's how it works in the fingers, at least. So you get a really tight fit of the grip.
Mm-hmm. Okay. Why do we keep seeing the Fibonacci sequence in nature over and again?
Math.
Math just kind of indicates that that's the way branching functions work and growth and everything else.
It's math.
Yep, it's math. Yeah.
Okay.
So let's just go back to the reducer for a second. So you see the reducer forms kind of this T that connects into the Y section of the joint that it's connecting to. And that little black screw that you see in there is sort of the axle or what that might be connected into the output shaft of the reducer. Now, the actual motor is aligned with the axis of the finger. So that means the motor is actually rotating along the axis of your finger in the wrong direction. And so it's spinning up this way, and you want to get it to spin that way. So that means you got to do something to take that rotation and convert it in a different direction. And we see this all the time in the differentials in our cars and stuff like that, right? We have the shaft that's coming out of the engine to the back of the engine, then it splits off and goes that way. So there's many ways of doing it. I have no idea how they're doing it. They probably could be using a simple bevel gear or something like that. And the advantages of that is not only can you change the direction of rotation, but you can also put some sort of gear ratio in there as needed, so you can get much higher torque out of it as necessary. So they've been able to miniaturize that. I mean, if you think about it, you'd almost look at that as like something like, what? There's some sort of shaft and gears in there. It's like, yeah, there's got to be. Yeah. So I'm pretty sure that's where it is. They may come back and tell me that I'm all wrong, but that's kind of my guess of what's happening there. And again, like the next two kind of rings that are in there are probably the actual motor itself.
Okay. So can I ask you a question right here? When you talk about miniaturization, how difficult a problem is it to miniaturize something like that and yet keep it robust?
Oh, yeah, it gets hard. I mean, it's at that point, you're dealing with things that are very fragile and break very easily. So, I mean, just think about clock makers. It's really easy to make a big clock, but you want to make a watch, boy, it gets harder and more delicate, the instrumentation that you need. It's not that it can't be done, but it requires a certain amount of skill to be able to do it. And again, because they're coming from the appropriate background, we know how to make motors. we've been making, better motors than our competition because we have the secret sauce that we know how to make the windings a lot tighter. And as a result, we can miniaturize, and they probably realize, hey, what can we do with this? Oh, we can build a hand. So they may not have like all the hand expertise yet. And so Gustav and I will try to go in and give them maybe some coaching and some ideas. But from the standpoint of building these electronics, way above my pay grade. And they seem to be doing an excellent job. So, we just kind of go down here and we see, again, this is a static piece of metal, which is just forming the rest of the hinge on there that connects between those pieces. So you can think of that phalange is kind of like a hamburger or a sandwich. You've got the meats in the middle, which is the motor, and then the bottom part, which is an inert bun, and the one up above, well, it actually does a little bit because it's got the reducers in it. But for the one below it, you see they kind of turned it around and said, well, wait a minute, what we're going to do is we're going to put two motors together to make the proximal. And that means something has to go here to make it rather interesting. And that is, again, let's remember, here's the names. There's a distal phalange, the middle phalange, the proximal phalange. And we're going to look in at one of them. And I want you to see here, so we've got two motors, and we've got this blue arrow up at the top, which is the pip joint right there. And then we see along here, the black axis. This is the axis of rotation that each of those motors is going to be rotating about. And then we see the next output shaft here, and the yellow is kind of perpendicular to the blue one. So in other words, we've gone from like kind of a flexion joint to now this is the abduction joint. And that means the output is in 90 degrees different from that. I'll talk a little bit about what the coloring of this is down here, but a part of figuring this thing out is we didn't have any like good views around the back, but we do have this view on the side. And you notice the motors have this kind of brassy color thing on there. I believe that's the cabling that goes from one to the next. And you'll notice that the motor at the top of the proximal and the motor that makes up the medial are kind of on this side because they're aligned in the same way because their axes, their output shafts are in the same direction. But it's kind of missing over here. And I think it's because it's been rotated 90 degrees and it's behind us. We can't see it. To get the output shaft. Now, the reducer had to be changed just a little bit because the geometry is different. But for the most part, I think that's a signal. It's like, yeah, they rotated that thing 90 degrees to get that in there. So that's why the output shaft is in this direction. The other things that you see now, I believe that is not structure. This whole black piece and the black piece down there, that's all structure and a hint of what's going on. This here is just some way of getting the cabling or wiring, if you want to think of it, around and going on up there because it's got to come from somewhere. Now, we already see this part up here, the kind of the black circle with the silver piece in there. That's the abduction. And then just below it, we'll see there's kind of another black axis along here. That's what's making the flexion. And if you look at that, you're like, oh, how are they actuating that? Because it seems to be different than the others. We have kind of a reducer going right in there. You're like, that's a mystery. How are they actually getting that thing to move? And we don't see anything around the backside, so that we don't see the top of the palm to be able to tell. But I can pretty much guess how they're doing this because this is the only way that makes sense. So what you're seeing here is basically a lever, only the part of it that's going on here. So we have the axis, and we have a lever that's popping out the other side that we're not seeing. But when we look over at this side, it's kind of revealed a little bit. It's right down here. And basically, I've highlighted them right there. So just keep your eyes on those two black pieces there. They basically are levers that come up into here. And what happens is they're connected together like this. So that purple thing that I've highlighted, that's probably where the motor is and the reducer for that. And the output of that reducer doesn't get connected to this little piece here, this yoke, but the output of that is actually connected to that black piece back here, which you can't see, but is this red link. It's that little red link I got there. Now, that red link is then connected. So that's the output. That's basically the output link. This here is like an idler link in here or connecting rod, the green that goes up to the next one. That's the blue one up at the top. And these little dashed red axes are basically showing you the axes of rotations that both of those are going to end up doing. So the output shaft is this one down here and up there, and you see the parallel. So that's basically a parallelogram. And if you build a parallelogram like this, and it happens in robotics all the time, especially back in the 80s. You look at a lot of robots, they'll have these back links. So long as the links of all of them are the same, of the blue and the red, it's a parallelogram, which means the angle of rotation of the red causes the same angle of rotation of the blue. There's no mystery. The math is like super, super easy to be able to do that. If they were different lengths, then suddenly like laws of cosines and laws of sines get involved in some nasty trig. Okay, so that's, I believe, how they do that.
Is it more, so why aren't they using a similar type of flexion as they do in the PIP and the DIP joint? Would that be too tricky, or would it be too far away from the ab and adduction or the rotation?
I'm just wondering myself, why not? Why not do the same trick that you did up here and directly put it on down there? It seems like it would work.
Or you're pushing the abduction too far away then that they couldn't get
it. It may have been something with a kind of a packaging thing that they just decided in order to get to where they wanted. Oh, sorry, I'm moving away too quick. But that's the way they're actuating. I'm not sure why they couldn't have done it kind of like that. And it may have been that when they started to actually build all these things, you just realized that we needed that gap in that room in there.
So this is kind of opposite of the way I wanted the people to start actuating the ab and adduction. I still thought as an anatomist and having those muscles in the palm. And here it's like the opposite, that they have it in the phalanx and they have the flexion in the palm. But the end result seems to be the same. So
yeah. It's so what you end up is you have a type of remote actuation here. For that particular one, and it may just also have a lot of things to do with how they're able to package and get everything in there. That I'm sure they gave it a lot of thought and maybe thought they could do it. Oh, why not just do it this way? And they're like, man, we just can't pack it in there. Is there some other way we do it? So that's probably what they came up with. It turns out that while I might be complaining about not having good views of the backside of the palm, or I guess you would say the top side of the palm, it turns out there are other sources than just this video, that if you actually go to the Pan Motors website, you will end up finding this brochure right here, and which gives you a lot of, sort of hidden details that we did not see in the video, that clears up some of the mysteries of what's going on. I'm going to go through that a little bit. And so there's also some nice specs in there. But the main thing is there's these two smaller images up here, which are kind of key to being able to solve a lot of what's going on. Not just that 4-bar linkage, but also how they're able to get the actuation at the IP joints. So if you look at this image, you can clearly see in the top of the knuckles, there's something funny going on in the back over there. You can see those 4-bar linkages, in one case in kind of an activated mode where you see the fingers being clenched, and also unactivated where the flexion is back. Now, if we look a little bit closer in this one, it becomes a lot more clearer that right above the knuckles over where the MCP joint is, you can see clearly a 4-bar linkage in there. But before I do that, what I want to do is go back a little bit further, because this image tells us something a little bit more of what's going on. And that is, if you draw a center line through the center here, which is going to be where the axis of rotation is of the motor. And if you look at the output shaft here, that's that red, that's the pivot point of where the IP joint is. You'll notice they're offset a little bit. And that offset sort of helps resolve a little bit of a mystery of how are they taking the rotation along that black axis and then rotating at 90 degrees to come over to rotate about the red. And there's usually two ways of doing that. Typically, you could use something like a worm gear, or you could use a bevel gear. Now, I want you to notice that if you look here in the worm gear, you'll see where the central axis is above here, that where the worm gear rotates, and where the output gear is, you'll notice that the axes are offset. So there's definitely different locations there. So the pivot point there is no longer along the central line of the rotation of that shaft. But if you look at over the bevel, actually the two axes of rotations do kind of align up. The problem is the output gear, the bottom gear here, would have to be kind of offset away from that center line in another direction. And so if we actually look kind of close at these IP joints, and what I've done is I've highlighted these sections here in yellow. So this is the yellow, what they usually call the yoke, this Y-shaped kind of output. And you'll see where the input is here, this T-shaped and T-colored, where the reducer is, and how they fit in there. And you'll see how symmetric it is. So if you would put a bevel gear in there, usually there would be kind of an asymmetry in there because that bevel gear has to be to one side or another to make space for it. And it just doesn't seem like there's enough space. Now, sometimes you will see yokes where it clearly is much thicker on one side than another. So that's why I say, I don't think they're using that. I think what they're doing is definitely taking like this worm gear here, shrinking it down to kind of fit in there. Now, that looks like a pretty tiny worm gear. Now, you just got to remember, worm gears and the output shaft, all those can have a different ratio. So this is just like an image I have out there. So if you reduce the radius of the output, you would be able to increase the size that worm drive to be able to fit in there. So it's possible that's how they're doing it. And you also notice there's a lot of extra space up above there. And some of that is probably to get whatever they need to be able to make sure that the drive is being held into place, because you're going to want to make sure that it's well seated on both sides to keep it from moving around. So that's my suspicion. There may be some other tricks to doing it, but that's kind of my guess on how the output shaft is. But now we can also look a little bit further at the knuckle, get an idea of what's going on there. So the close-up of the knuckle, once again, we can see, as I kind of suspected, that you have these 4 pivot points. So this red down here is basically going to be the input rotation that's being connected to this linkage here, which then causes a rotation about the green and about the blue, and then eventually about the purple around here, which is your output that's actually going to do the flexion. And, Gustav is speculating. It's like, why didn't they do it the way the other ones were for the flexion? And that, we were just kind of thinking like, hey, well, why would they do that? I think this confirms a little bit that it is a packaging reason for one more reason, which we're going to see in a second here. First, I complete the diagram here so we can see what's going on. And even though you see these funny little dog legs here and these links, don't be fooled by them. You have to look at the axes of rotations. That's what really determines the geometry of what's going on, not the underlying way that they actually built the mechanism. So these pivot points pretty much determines the geometric relationships. It looks like it's a parallelogram to me. But again, why would they do that? And I think part of it is if we look here, you notice how the palm is a little bit thicker than the fingers. Yeah. And in the palm is where the motor is for the flexion that's happening about the MCP joint. So I suspect that they probably have bigger motors in there. And as a result, everything's a little bit bigger. And then trying to get them, the output shaft and everything is going to be a little bit oversized, which means you're going to have a misalignment between the abduction and the flexure. And that's what Gustav was just hinting at, that, well, maybe it's because they don't want to have such a gap there. And I suspect that's the reason, is that they have something that's a little bit oversized there. It's much tougher to keep both those axes lined up. So the way we can kind of confirm that is, again, this is one of the images from their brochure. I know it's all in Chinese, but I'm going to blow this part up right here. You can put this into chat if you want. And that basically is saying this is what the output torques are. So the output torques at the IP and MCP joints are 0.3 Newton meters and 1 Newton meter. And basically what they're saying is that is at that knuckle, it's got 3 times more torque coming out of there, which probably tells me it's a bigger motor there. And that would also make sense, because when you go to grasp something, that's probably the most important one. So as your fingers kind of curl up, something like this, to grab something, it's really the torque that's being applied there. These other two, well, it's nice to have something to be able to hold something better. It does not need to have the full torque to be able to lift something as heavy as like 10 kilograms, or I think it says 10 kg here. They were showing in the video, it's actually like 20 kg that they were able to lift. Yeah. And that would make sense, is that you want that particular joint to be more powerful than the others. So,
so this is per finger? This is per
the load? Yes.
Okay.
That would be per finger.
If you take 4 of them together, the weight is distributed between them, right?
Yes. So that means
discounting the thumb.
Yes. So the thumb would come around, and then from the Newton meters, and it depends upon how far off you are. I mean, the further. So if you're trying to do it in your fingertips, it's going to be tough. But if you're actually doing it closer here and having it laying on the proximal phalange, then the moment there is going to be a lot less, and it's going to be a lot easier to be able to hold it. But obviously it's way out there. But the main thing is the rest of your tips, they're not really carrying the load. The others are just there to kind of curl around your load to make sure it doesn't slip off. That's all. Right. Most of it is being taken right there at the crease of your palm. All right. So I think that solves a lot of the mysteries of how the fingers are being actuated.
So before we leave, so you
Mhm.
talked a little bit about the electronics, but how won't the cables snap after a while with repeated flexion extension, or are they so integrated into the joint that it's
It
protected?
looks like they're so well integrated in there that they work well. I'm actually
Because there
amazed
has
at
to
how
be a
the cabling.
cable there somewhere, right? It can't
Yeah.
just be like a connection between the metal parts that kind of
Yep.
transfers it has to be a cable somewhere.
Yeah, it's a cable, and it looks like it's a type of flat flexi cable that's designed to withstand the rigors of that. So it's really quite an interesting solution that they've come up with. And so I'm pretty sure that what we're seeing is the cabling around the abduction joint right there. Okay.
My first thought was that there were like small circular batteries in each of these phalanx that they have to screw open and put in there, and like you have to change your small C2032 or whatever they are called.
Yeah.
I just want to now go back to my question that I wanted to ask you about the distal phalange. If you can, so observe the shape of it. So I just want to bring this up. Give me a moment. I'm going to bring up the apex hand. Now you have a lot of tactile e-skin on this. You also have the ability to sense pressure, and there's I think a frame later on. Now here you got soft fingertips. Now take a look at this and the shape of this. So we see the Wuji hand with the glove. And without the glove, if you go back to it, observe the shape of this, because you've got fingertip sensors here. And let me now bring up the Wuji hand.
What we don't know is enough about the glove and how the padding in that glove is designed. So I kind of know where you're going, is that at the distal phalange, right?
It seems to me that there's space for some sort of sensors to come under the glove a bit later.
Or a little pulp. So it looks like it's designed for a little bit of meat to go in there to either make it kind of soft, or like you say, could be some sort of sensor. And on the other side, we're seeing hints of a fingernail. Now, that fingernail may be covered by a glove, but they may eventually be thinking, because I'm looking at the way that fingernail is designed, it's almost like something could go around it. So they may have come up with a way to actually expose the fingernail once they put the glove on there, or planning to do that. That's sort of my feeling is, and that's a great idea, because now they can get what they need for being able to pick up difficult objects like, like needles or coins or something like that without it. So that probably one side is going to be very pulpy and the other side is going to be very hard.
Yeah.
So do you think
last time, Gustav, you explained pulp to pulp and pulp to nail to us, and why it's important for picking up fine, small, sharp-edged objects?
Yeah, I think everyone has tried it, especially if you have cold fingers, that you need the support of the nail to kind of get it. And also, if you don't have a nail, it wouldn't be an issue for these robots. You could design around it. But if you remove a nail from yourself or someone else, the pulp will move unnaturally for you, and it would be much harder to get a good grip. So the nail is important to counterforce whatever is pushing on the pulp. But I'm wondering, are they really focusing that much on the glove, or is that just like an aside? Oh, we also have a glove, but we're focusing on the actuation and the robot, because the glove looks a bit, I don't know, prototypey very early.
I think so. I agree. I agree. I think it's prototype with the idea that we want to come up with maybe a better covering around this eventually. Yeah. So, but as you can see with the glove, there was no pinch points in there.
No.
The other gloves that we've looked at, you can see there's all those pinch points between all the IP joints, and this one here just covers it up really quite nicely. And let's see what I do. Okay, so now what we might want to do is, of course, here we're seeing it in the abducted position right here pretty well, but a lot of it is to look in on the thumb. So the thumb is pretty interesting, and as we kind of look in, we can see a little bit about how it's mounted. And the first thing I think we kind of glossed over is the degrees of freedom of this hand. This is a 20 degree of freedom hand. So they have 4 in every single digit. So obviously the 3 fingers, we've got the IP joints and the MCP, which is 4 each. So 4 times 4, that's 16. That means 4 is left over for the thumb. However, the arrangement here is a little bit different. So the previous ones, the flange below basically carried the flange above. Now the flange is carrying itself. So the first thing I want you to notice here is that, boy, that has a well-defined thumbnail. Even if it's getting covered up by a glove, I think there's going to be something about the way they design the glove and put it over there that they will either want to expose it or have a very thin layer on it. So it's there intentionally, that's for sure. But you can see here that whole distal joint has, for sure, a motor built in there, because we can see the cabling and everything else going around there. The reducers over here. So they build the thumb backwards as opposed to the others. All right. Now, here's an interesting sort of side view of the thumb to see how it goes together. Again, we can see up at the top where the distal is, and then where the middle, and then down here where the proximal is. And then
we the metacarpal for the thumb.
Right. So I guess that's technically the metacarpal, right? Yeah. It's and then we have what is attempting to form a CMC joint. And I'm trying to think, is that okay? Yeah, I went ahead and put some arrows on here to make it a little bit easier. So we can see the green ones is what is technically supposed to be the flexion. And then the red one there, I guess, is like it's perpendicular to the green. So it's a kind of abduction. And then we have this blue, which is, you'll notice, is kind of an interesting position. I think if we look here, going back to this original one, you'll see the way this is mounted. It's not mounted, let's say, horizontal or in a perpendicular. It's like it's intentionally askant there for a good reason. Now, when we talk about the degrees of freedom in a hand, if we ignore whatever is going on in the palm with the metacarpals, usually it's considered that the thumb has 5 degrees of freedom. That in our CMC joint, we have 5 there. That's pretty standard, what everyone says that. Yeah, it's got 5, where these guys up here are 4, which is why you get 21. If you want to do this thing, you can say 22 or whatever. So that means there has to be 3 down here. So that you're able to rotate in every direction. And we saw in the last video, I think it was the Dexel hand, that when that thumb was pointed at us, it was able to rotate. Okay. Which is really weird, because I can only get my thumb to rotate by doing something like that. It doesn't naturally want to do it. And I challenge anyone to try to get their thumb to do it. Now, the reason they did is they wanted to get 3. Yeah, they wanted to get 3 degrees of freedom there.
Yeah. Now, your thumb will rotate a little bit. I promise you. If you hold it like this and look at the nail, but you can't control it, but it will rotate. And then when you flex the MP and IP joint, your nail will rotate away from the palm.
Yeah.
So, but that's built into the joint. And now when we have hinge joints, that's not going to happen. But naturally, your thumb will rotate a little bit when you flex it. So the pulp is closer to the palm when it's flexed, whereas when it's straight, the nail looks straight at you. So that's kind of like the condylar design of the MP joint, but also the IP. Of course, down here is where we do most of the opposition, but there is a little bit of rotation as a result of the joint design, which we can't do with these bots. So there, perhaps they
exactly. Like, okay, it's a type of coupling that's going on in there, and a lot of it comes like the order of operation, that you can build something to say, I'm going to use Euler coordinates of some sort, yaw pitch roll or something like that, and you can have one of your axes of rotation maybe along that, but you can also set them up to be I'll have 3 axes of rotation, but I actually won't have one of them pointed right along that direction. However, if I get the right combination of those rotations, I can still get it to point in any direction I want, but it may not be very easy for me to say, just rotate it about there. I'm going to have to do some weird things. And my feeling is that while we say there's 3 degrees of freedom down here at the CMC joint, I think there's like, there are like 3 rotations, but I don't think they're all orthogonal to each other. And as a result, you don't really have the full range of motion in there. And I would argue you have more like 2.5 degrees of freedom, because you have, basically, what is it? The rotation that we naturally have is a bit different. So while it seems like there's 3 degrees of freedom, you're kind of limited on what's happening. And that what they're trying to do is, if you actually look back at the joints, and I'm not sure that we can see they mounted them a little bit funny here. So if I go back to the to where I put these things in here, this axis seems to be perpendicular to the green axis. But when I look at it with the blue one, I think it's like almost intentionally rotated a little bit off. It's like they're somehow trying to capture the natural motion of the thumb as best they can with those 2 axes. And I think you almost can, because as Gustav said, it's like as you do it, something just kind of happens naturally. And then it may be there is some kind of cam or other mechanism you could put in there to get that rotation that will be a bit closer to what the thumb actually does. Because I look at mine and I almost convinced myself I only have 2 axes down there. I really don't feel like I have 3, but every source I look at is trying to convince me I have 3. So so that's kind of what's going on there. And so that's my part of the presentation as far as the mechanics. Now I've got a bunch of images here that I think we want Gustav to start talking about. And this is like the first one I captured. What do you see going on here?
Yeah, so this is the first step of them trying to recreate the Kapandji score, I think. So similar to the Apex hand that we looked at yesterday. I don't know. We take credit even whether it's not due, but I mean there.
Well, we'll just take credit. We take it.
Yeah, we'll take credit. So we talked about Kapandji almost a year ago and kind of explained it. And you asked, are there any robotic hands that can show their score? And now it's starting to appear. So what these guys do not manage with what the Apex did is what we were just talking about, the rotation of the thumb or the actually getting the pulp to pulp. Here they're actually touching the side. So and it's doing it for all the fingers. It's still reaching the little finger and it has a nice like hole for the opposition, but it's not pushing against the pulp of the fingers. And that is, I think, partly due to the way they designed the thumb joints and also the length of the fingers perhaps, but these guys manage. I think it's primarily the rotation of the thumb that the Apex hand has that gets it to really be able to touch the pulp, whereas we have, similar to this rotation of the nail in the MP joints we have and the IP joints of the fingers, there is a natural rotation of the fingers going in towards this meeting of the pulps. And then, as I often mention, the fifth and fourth metacarpal has a slight rotation and flexion that also opposes the little finger a little bit. So there is inbuilt slight rotation in the joints as reflecting them. And there is also the movement of the fifth metacarpal. And then also the thumb has like rotates out the nail a little bit so that we can reach pulp to pulp. And so now we're at the level of the real, what we call prehension. Like, can we pick up a nail between the pulps of our thumb and the ring finger, for instance? We can use it when we're tying shoelaces or whatever. And this robot with this setup doesn't seem to be able to do that. You will have probably a really nice strong grip with the lateral prehension or lateral grip, but it's not really a true Kapandji of wherever it reaches. I don't remember if it goes all the way down, but it's good. But now we're reaching A tier here now, so we expect more.
now I think they were trying to go for like a Kapanji of 20 here, because that particular one is not considered one of the scores you put on there. And this is a question that I have for you: I'm not quite sure how the Kapandji works. Is it the outer part that you do? Because it looks like in the diagram, it's the outer and not the inner, right?
Yeah. So the index finger, it's outer, and that's probably because he wanted to kind of evaluate how well are you grabbing the key card, which is, or the lateral grip with the thumb, which is important in our everyday life. And then it's coming to this, can I grip things between my fingers and having a stable grip? So for the middle ring and the little finger, it's just a pulp when we're up here, and then you go down the little finger at the creases or at the palm side of the finger.
Is at the creases. It's not on the pads.
The creases, no. Yeah. Or I guess it doesn't really matter if you're on the pad or crease, but it's easy to find the creases of the distal IP joint, the proximal, and then this is not really a joint, it's just the crease of the proximal phalanx, whereas this is the MP joint crease. So we get kind of tricked when we look at our fingers and we think that this is where the joint is at, and some of the robotic designs have done that. So they kind of put their joints at this crease, but this crease is not at the joint. The joint is down here at this crease of the palm.
Right.
So that's the final point of the Kapandji score. And to have a real score, it needs to be true opposition, like going across and reaching it. And reaching the palmar crease, it will of course not be a very big opening, but it's still a true opposition. It's not, as some have shown, a flexion of the thumb when you flex it into the palm. This is 0 points on the Kapandji score. It needs to be a the thumb needs to be in anteposition and then reach it over to do a full opposition. So there are some, you could kind of, and the patients, when they have a nerve injury, they will have this problem. They can't do opposition. If you have a median nerve injury or a really bad carpal tunnel, you lose this capability. And they, when you ask them, can you reach the little finger? And they will do it. They will kind of trick you because they go with a flexion. They don't oppose the thumb. They just go across because they want to be good patients and show that they can do what the doctor asks. But this is not a good grip. You won't be able to grasp an object with that flexion. It will just kind of go into the middle of the thumb. So there are some minute details that will become important when they're going to train to do real grasping tasks.
Yeah,
and
let's just go back to the video and take a look at the movement that they're showing us here.
Yeah.
So there you go.
So they're like adding and a third for each Kapandji point.
Right. So,
and what was the fun? Yeah, they go to the tip of the little finger, right? That's where they stop.
Yeah.
This, I think.
Stop right
So,
there.
and that is it's a little bit of deflection type. It's not as fully opposed, I think, when they're doing the last one. But maybe they're not trying that really, since they are going. Yeah, there they manage.
And I'm not sure if the thumb can make it all the way over there either. So it may
kind of
be at its limit. Right.
Yeah.
Now, the other day you were talking about the thumb and being able to have the thumb go behind the palm to be able to lift up. We're not seeing it here, but they may be close. I think they can at least have a flat thumb. It looks like it will be pretty close.
And so our thumb is positioned a little bit forward in the palm, so that it goes into the palm in a similar manner to this joint design. But I don't know, it's hard to see on a 3D plane, but it is pointing towards like the base of the third ray. So it's not in parallel with the second finger. It is a bit more bowlery, but we can still like retro-pulse or retroposition the thumb quite a lot. And some can score it by how high up on your other hand can your thumb go. Is it the first or the fifth metacarpal, the fourth, the third, or the second? And that is important in grasping things. And a common injury after having a radial fracture is when the patient comes back, this tendon that performs this task has been broken, so they can no longer do the retropulsion of the finger or retropositioning of the thumb. It's the same tendon that will extend your distal phalanx on the thumb, the IP joint of the thumb. It's the same one that lifts the thumb up from the table. And it might not seem like much in your unless you lose it. You don't know what you have until you lose it. And opening up your grip to grab something. So I'm not sure. We can't really see in this video, I think, how good it is at that. At least it gets it out to the side. But another thing with the thumb, I think this hand will probably also have, it will be able to adduct it, of course, but I don't think it will go all the way in. So our adductor, the muscle that does this motion, it has the origin of the third ray, as most things do. So it pulls almost all the way into the middle finger. It doesn't just go to the side of the index. The muscle pulls all the way in here. And it's the same in other primates, that's where the muscle originates and then goes out to the thumb. And I think quite a lot of the bots will have issues with this because they put the joint maybe too far, as I showed previously. You put it parallel with this, and then it can't move it all the way in because it's supposed to be a little bit in front to be able to reach the side.
I think if you put my image up right now, we can kind of see where it's mounted, and we'll see it is a little bit off to the side, as opposed to really being kind of down there where we'd like it to have. Have it be. Now, I think a couple other points that will be interesting here is that the shape of the palm,
I was just coming to that,
better than most.
It seems,
I mean, if you're not
the cupping part of your palm seems to be pre-built into that.
Exactly. So and that is the natural position of our hand, or I don't know if the English term is correct, but resting tonus or vilotonus, we call it, which is like the resting state of the muscle, how it's tensed up. So the thenar and hypothenar will create this natural arch that is always there. Whereas if you have a loss of innervation of this muscle, the palm will flatten out to look more like the apex hand.
Right.
And if you're going to catch things, it's good to have that cupping. And if they're not even attempting to as these guys have not done yet, at least, if they're not attempting to get actuation of the thenar eminence and the hypothenar, so this part of the hand, if they're not trying to emulate that, then it's of course better to have a natural cupping there. But then there might be issues if it's gonna carry something flat, so it's always like this. But if you put like a plate on your hand, your palm will flatten out to get a lot of connection points with this glass or this metal tray that you're carrying. And this will be less connection points, or whatever you would like to call it. And
contact points,
it might be less stable than if you could actually like flatten out your palm. That's how we get a good stable support of carrying a tray. Whereas if it's like this all the time, you're going to be really wobbly. Maybe they will carry a tray like this instead. I don't know.
Yeah. Now there's one other thing.
Soft. Is that material possibly soft in order to?
Yeah, to kind of even out, maybe.
It's hard to say. I assume that's kind of a rigid plastic, but then they have the glove going over it, so the softness may come.
The glove will kind of
so that might be stiff enough to be able to kind of protect everything in there, but create the shape that they want. Now, speaking of the shape, we are seeing how the hand is making that nice little arch along there, but it seems like the mistake everyone is making is they assume, we'll make the arch. They don't realize that sort of the default position is these joints should always be kind of pointing in. Yeah. And I think that's what you referred to before, Gustav, is that it's because of that allows you to kind of bring the motions in this way. Whereas if you're designing all your fingers to really be parallel, in a sense, you've lost that. And they kind of missed the opportunity here that all four of those motors you'll see are up parallel, and that maybe what they want to do is actually kind of radiate them out a bit to get that more natural motion.
Yeah, because with this design that they have of putting the actuators next or integrated into the joints, there can't be that much in the palm that needs space. I mean, maybe there are something that the cable is connected to, I don't know, but it should be room to kind of.
I think it's hollow because I think the lower, there's almost nothing below here. That, if it's the same actuators up here and that particular actuator, what I'm thinking is that maybe they could have a slightly beefier actuator down there because that one is being used for the flexion.
Yeah.
And maybe that's why they have that back link, because they might be saying, that's the one that's most important for the grip strength. The others, we can't make them that big because they got to be up there. But still, I don't think they're coming down that far. So I would not be surprised if that is a slightly bigger actuator they decided to put in there. Now that would explain why that linkage mechanism in many ways to be able to get away with it. But still, they missed that opportunity to get them angled a bit better so that when you have that flexion, you're able to bring them in to create sort of the proper shape.
Okay, I have a question. What do both of you make of the morphology of the palm, the dark area? It's not smooth. It's kind of undulating. Is that for grip? Is that for structural
I'm thinking
extension?
It's catching the ball, like grasping certain objects. I think that's why they're emulating it, or perhaps also to house the thumb, and they just look at a hand and say, okay, it should be arch. Perhaps there wasn't any more thought and like reasoning. It was just, this is how it's supposed to look, so that's why we're going to emulate. Whereas when I was a bit disappointed with the apex hand, which is also very movable or has a lot of control, it has a very flat palm. And maybe they chose that, it's going to be able to push things and grab things from the side, so we need a flat palm. I don't know. So this is more
just for visual
context or human life. So this is very, at least in these images, it looks quite flat. It might
very
be
flat.
The color that tricks you, but so I guess it's perhaps you can't have both unless you actuate it down here, and then perhaps you more or less decide. And perhaps that's also the reason why they don't angulate the metacarpals. They are parallel. Is that when you're gonna grab your I don't know, your stick or your barbel, if you have it like this, perhaps it's trickier for them to kind of get a good strength in the grip. Instead, especially if it's always like this, they have to activate their adduction before grasping the barbel. And then when they also have the same length of all the fingers, it's even more, I don't know, if it would be like this, it would kind of intersect with each other in a way that's hard to I don't know, get around. So maybe they've tried different versions, or it's just that this is the way that they shows it. It's like we put them parallel and then but here it looks good. I mean, and I've heard others say that, oh, we don't really need the fifth or this motion of the fifth. We can emulate that motion with the displaying of the fingers or the abduction. If you just have the motion correctly, it will look okay.
Yeah. And yeah, so this is the range of motion of the abduction that they're showing. Is that about normal or a bit more?
I think the index finger is the one that we can move the most. I think it's said to be like 30 degrees in each direction, or maybe it's a total of 30, and then it kind of goes down. So our pinky is not very. It's a lot. It seems more mobile here than our pinky is. But to kind of compensate for the fact that the metacarpal is not slanted, it perhaps needs to be able to abduct even more to reach that position. So it seems a little bit more than what's normal, but I don't know if that's a problem in itself. It's at least not less than what we can do. So.
Okay, so
but
you get that
really,
large.
The length of the finger really stands out here, I think. It's like a inverse campodactyly where you have a short finger. This is like the inverse. Macrodactyly is like a condition where you have bigger fingers than you should.
So now the 20 fully actuated rotary joints, that's what we've seen. So we know it's 20 degrees of freedom. And they're showing off here that because of that, they can get all the different gestures that you want. So you can get the full kind of clawing motion or even a straight finger. And I think and
okay. Do the individual
individual.
Which some can kind of get that motion, but it's not something normal people do. But it's nice to have that. I really like that they have that control, because then they will be able to do the fine motor things. I think, like kind of if you're gonna draw with a pen, when you push the pen forward, you need to kind of straighten out your IP joints when you draw on the paper, whereas when you pull it back, you flex it. So it's not just putting it with your forearm. Your finger moves when if you're drawing a line on a paper. So they can do that kind of motion with these individual actuators. So that's good, and it goes for all things like playing the violin or the guitar or the piano. Is like when we strike a key, you flex or extend the MP joint with the long extensor, and you flex it with your long flexors that come from Elon's favorite place. But then when you strike the key, you use the interphalangeal or the intrinsic muscles to extend these joints, bang, to hit the key of the piano. We don't write on the computer like that. That's more of the old typing machine, perhaps. But when you're playing the piano, that's like the striking of the key is using the intrinsic muscles, and this bot will be able to do that, I think. Whereas the Tesla bot will have big problems playing the piano. So no intro to Westworld with the Optimus.
At least with the version of the hand
2.5 hand, Who knows?
Maybe. Now this here is, I think, a very important slide. Simple kinematics, minimal sim to real gap. I absolutely agree with that. Because you don't have to worry about what's going on with tendons. You don't have to worry about coupling everything else. Everything is serial and is in there. They're basically like tiny little robots is what they've turned the fingers into with extreme control.
And with this the thing we talked about, the passive joint. I mean, and maybe that's where the clip of this we talked about previously, where the mathematics of 3 joints when it's like spinning all around. Now you don't really have to calculate for this distal joint flexing just because the middle joint is, or the middle phalanx is flexing. So when the string is connected out there, but it doesn't really have to be. It could have been connected here, and you would still get this flexion of the finger. And when I extended with this, it will follow along. And that I imagine would be harder to kind of simulate or
it's very hard.
And now you can directly just
we absolutely, because what you can do is that as you're pulling on that, It's taking a certain shape when it's not under load.
Mhm.
And if you put like a load here, a load there, suddenly your fingers are going to bend different.
Yeah.
And that's what's the challenges with sim to real, is that you might be saying, well, I know it's going to do this, and then it comes in contact with something, and now you're not quite sure which of these two IP joints is kind of flexing back or resisting that, because that little contact point. And then
That's
now
true.
I need to oppose that force in some way. This thing here will have no problem.
No.
It's going to know where it is, and it's going to know a couple ways, because I think at some point there's a slide in here. Well, first we see that these are brushless servo motors.
What does that mean?
They don't have brushes. Well, actually, brushless motors are good. That basically means they don't have servo. That the brushes were a way of being able to get power to the rotary part. So basically, you had like the wires coming in, and then you had the spinning part there, and it would have these contacts. And a brush was basically something with a spring that would be pushing against that allow the power to kind of get into it.
Okay.
And then those brushes would wear out after a while, of course, as you went around. And the thing is, you kind of invert everything around, and I guess maybe put the stator technically on the inside or something like that, so you don't have to conduct power into the other side. So brushless basically means less maintenance as well. You're not creating dust, because these things wear out after a while as you're going around. Now, and of course, I have 1,000 hertz communication bandwidth, which is pretty good for being able to do the control. And I think at some point, they mentioned this. 20 output encoders and 20 input encoders. That basically means they know the position of the motor, and then also on the reducer on the other side, they know where that is, because that is actually telling you where the joint is. And I guess it's kind of important also that if for some reason you lose power, or when you want to reset, you want to know the relationship between what the current encoder is on the motor and what it is also on the output of the encoder. So those are the outputs they have that allow them to do the control. No other sensor that we know of, but they would be able to feel through back EMF and other things, sort of what the force load is, or what the torques are that are on there. You get a better idea to be able to control it, which again helps in that sim to real gap.
So does it? How much does it tackle the need for sensors?
Oh, I mean, it's still going to be nice to have sensors in your tips. It could be you can get away a lot just by having cameras so you can see everything like that. But, nothing beats having that fine feel that's on there. And again, I think they'll just find a glove. If someone's not working on a glove, someone should be working on a glove that will have all the sensors built in. I think I've already seen a couple that have something like that you can even wear on a human hand to be able to not only get haptic feedback, but to, yes, data. So that's another solution. And I'm glad they didn't, I guess, focus too much on that. They're really thinking about, let's get the actuation done, and the sensors will be able to deal with another day, but let's go ahead and do this. The main reason I wanted to show that is again, the clenched hand there looks almost human-like. So they really get that shape right. It looks pretty good. Even if the pinky's a bit big. It's like,
the pinky is not really going in like we do, but that's and if they, I have a hard, it can't be too tricky for them to kind of shorten the pinky a little bit if they want to make it. I mean, when you're producing millions of bots, of course, it's easy to just have the same for all of them, but then you might as well vary them a little bit, because you're still producing millions of shorter fingers. So then they would look even more natural, I think.
Yeah. And I'm sure this is a prototype. Now, I think they have at least two, because sometimes we're seeing what looks like a left hand and a right hand, unless they mirrored the images going on here.
That's true. When you saw the cable coming out, that was the left.
And then we'll see the thumb is pointing one way versus the other. But just looking at the knuckles themselves, not looking at the pinky, it's like, that looks pretty good. It looks actually better than all the other human or humanoid hands that we've been looking at. Teleoperation, and they were just showing how quickly that works. And as we can see, this impressed me, that when they were moving around with just two fingers. So you were telling us the other day how important the pinky is to be able to hold something. I was impressed. Like, wait a minute, they're doing that just with two fingers, and the other fingers aren't doing anything. Yes,
this barbell is
the thumb and the index. It's 5 kilograms.
I'm just thinking of when I.
Yeah.
If you go back, when I was a kid, I was in a play in school, and me and another friend were like the strong men, and we had these big barbells that said 100 kilos on them.
Yeah.
So does it say how much that weighs?
It says 5. It says 5 kilograms.
Oh.
It's a little bit blurry, but when you play the video, you will see that. And they're going horizontal, vertical, and horizontal and coming back. And it seems like it does not slide in the hand. I was pretty impressed with that grip strength with just 2 fingers.
Wow.
But is it because they
I'm
can't
surprised.
get the other 2? They should be.
Oh, I think they can. I think they can. I think they were showing off because here they show the power grip where now they're using all the fingers to be able to do that. But actually, that impressed me more that they were able to get a grip like that because, really our pinkies are so important to be able to hold something in place. And they must be using part of the palm for that. I just don't see how you get it with 2 fingers to be able to manipulate because it wasn't flopping around at all.
No.
Yeah, because the weight is resting on this part.
Yeah.
In this case.
On the top of.
So we got the power grip there, which looks pretty good, 20 kilograms. And again, the precision, not a surprise because these fingers are like tiny robots.
So, I mean, this I also think is because you asked for it. I mean,
yes.
We'll
take credit.
Actually, it's just something that everyone knows is tricky, so they're trying to show off.
Well, I will give credit to James Dalma because he mentioned it in a Robotaxi ride with Dave Lee a couple months ago. And I said, okay, James is kind of right. That's a tricky one. And so then I asked Tom Zhang, I said, okay, can your hand do this? And within probably 2 hours, he put a post out showing that he was able to grab with his hand. And ever since then, all these others are doing that and they're doing Kapandji. Now, the hand is very difficult. And I think what might be noted here is that first, why are they using a left hand? Because usually left-handed scissors are very hard to find. The other thing is the way it's holding it is kind of all wrong. That's not the way we hold it. So I want you to see is like, I'm going to try to emulate the same thing here is that first of all, okay, I guess I have to do it in my left hand. And then we have to sort of see whether my hand based on the screen, because everything is back. Oh, my hand is backwards. So I guess I have to do it with my right hand to make it right for what they're doing.
It looks right for us when you do it. Yeah.
Okay. So it looks, is this correct right now? Is that kind of
turn
line
it towards us?
Oh, okay. So maybe I need to, okay. I want to have my hand in like this.
Yeah.
Oh yeah, there we go. So it's kind of pointing the right way. So this is actually my left hand trying to do the same thing.
Yeah.
And you'll see that I have my index finger and my middle finger coming through and the thumb a little bit, but I have no idea how to do scissors that way. That's not the way I grab scissors. That's the way scissors are designed. They're really designed to be using your fingers in the back. And then you use your index finger to kind of hold it in place. And usually you want your thumb to come all the way through. And as we all know, when you're doing scissors, it's really not about getting them to close. There's always like a little bit of pressure you have to do. It's like you get your thumb in there and you pull on that thing to really get the 2 blades to come together. Otherwise, you do this and for some reason you don't get any cutting action. So
and I mean,
the
scissor grip that they're using is more like maybe like a child would learn how to cut or something, and of course it moves the scissor blades, the pair of scissors. But I mean, it's as you say, there is a lot of things going on in here and in the thumb, and not just these flexors that would be used otherwise in like the Tesla bot. So these guys would at least be able to kind of, I expect, to balance it with the abduction control and also the opening of the thumb and also the
and you have the surgical
of course. And this one is a bit old, so it's a bit stiff, but this is how we put the finger on top to kind of support it, but it's the same as if you put it on the side. So that is one way. And then if you want to do it left-handed, you do hold it like this, which I'm not going to be able to do it when I have to stand up. So it's like you palm the scissor and you use your thumb and index finger to kind of cut. So this is where you're like an assistant and cutting the needle. So here I need to push with the thumb to make the blades kind of push towards each other. Otherwise, it's really hard for a left-handed to use a pair of scissors like this, because it wouldn't kind of have that pressure that you were talking about. So you need to kind of push them towards each other. We're doing it naturally when we're using a right-handed scissor with a right hand. It will kind of push towards each other. When we push the thumb in, the blades will meet to cut the paper. Whereas when we're doing it with the left hand, we have to push down with the thumb and up with our finger to make these cut sharply. Otherwise, the thread will not be cut. So the left-handed, that's the next challenge. Do it left-handed with a right-handed pair of scissors. If the bot can do that, then I'm impressed.
everyone's wondering, is Royden looks like the Rock, as everyone says. I tend to give these very long, dry PowerPoint kind of things, which is like paper. And as a surgeon, of course, you deal with scissors all the time. So that's why our order is always rock, paper, scissors, like this. Yeah. Yes.
And I had to bring my micro scissors then in order to be true to my length, my height. I'm Tesla bot size, that I say. No, but this 10 micrometer precision, what did they mean? Does it mean that it can kind of hold it precisely with like 10 micrometer?
Yeah, see, that was like right down near the end, so I got to zip along everything here really, really fast. And I think the precision was better than 10 micrometers for repeatability. So that means
put in this position, put in that position, put in that position.
Basically, yeah. If you look in the video, you'll see that they release it and they go back up there and they get it very close to whatever is the reading that's up there, and so they can get within 10 micrometers every time for repeatability, which is pretty good. So repeatability is what you really want to talk about, not so much accuracy. Because the hand could be anywhere, but the idea that within that the hand is able to repeatedly go back to the same position again and again.
Because that's, I think, when you're saying, when as a surgeon, I'm not as worried about AI taking over, and maybe this is not what we're having to worry about. But I mean, they have to be extremely precise in their positioning, and not everyone is using microsurgical techniques in their everyday surgery. But what these guys, the bots will have, which we don't, is the stability. So I have a very I don't know if you can see it, but if I hold my hand like this, it's like it's shaking. So as a surgeon, you're supposed to have steady hands, but it's all technique. It's not my muscles or my control of the hand. I put the back of the forceps to rest on my metacarpal, and then I have it steadier. But even now, it's like shaking and moving. So therefore, I use these fingers to support, and that's when I can get the really steady point of the finger. So when you're doing microsurgery of small vessels, you need to have that support. It's not because my hands is more stable than someone else. You learn the technique. But these guys, they will be able to most likely kind of put it in this position and be perfectly still. Or is that incorrect? Or
no, they should be able to. It depends upon the kind of compliance that you have in the arm and everything else, because I don't think it's so much the hand that you're worrying about at that point. A lot of the shaking you're getting is because your arm can only hold it up so much. Yeah. So everything back here, but with industrial robots have no problem holding that.
No. Exactly.
In that position. The question is whether the humanoids would be able to maintain that, depending upon the amount of compliance we might want to have. But if it's a surgical bot, then it will probably be built to a different standard.
Yeah, and I mean that's
do you think of all the bot hands we've seen when we talk about fine motor movement and control, this is perhaps the most right up there, the top three, if not the top two?
There's a reason everyone kept spamming us. Oh, when are you going to do a breakdown on this hand?
Yeah.
There were a couple other hands that were out there, and we didn't see the same amount of people just saying, "Oh, when are you going to do a breakdown?" And I've a lot of people that in the community have been mentioning this to me as well. It's like, wow, what do you think of that hand? It's pretty impressive, despite the fact there were like 2 or 3 other hands that came out at the same time that no one really cared about. So, and I think part of it is that it really is not tendon driven.
Exactly.
And there are a couple others, the microdrives, but these drives seem like they have way more heft than some of the others. And I mean, this is a really good first attempt. Yeah. There's no doubt about it. There's some room for improvement, but it's good.
I mean, if it's durable enough, I still kind of, with my layman, I have no engineering background or whatever, and it's far away from the design of the human form when it comes to the muscles and tendons, but I still think that this would be a better approach to really being able to do sim to real and to emulate the small fine motions, to try to do that with flimsy tendons of different materials that will break over time. And this has to be a better way, I think, if you can get it to be strong enough and durable enough.
Yeah.
And I mean,
Sorry,
you don't have to copy the human design. I mean, you emulate the shape, the form, and the function, but you don't have to do it with parts of the muscles here and parts of the muscles here. In our anatomy, it has to be that way for us to get the power. We need the muscles up here. Otherwise, our fists and palms would be gigantic if we're going to be able to have the power that we produce with our forearms. If we put all that in here. But these guys perhaps can mechanically, you could get the same brute strength in the future.
Do you think?
And we talked
Scott,
before as well.
Tesla, do you think this time, or can Tesla switch if they want to?
Maybe they have. Oh, he's still talking about the tennis.
Yeah. Now a lot of these hands are available on the market. I don't know if this one yet, but some of the others are out there, and everyone is buying them and reverse engineering and trying to figure out what's going on. Now, the one thing is that there are a lot of tendon hands out there, but there are also a lot of hands that do not use any tendons. And the way they've managed to do it is that they've been putting the actuators in the palm, and then through mechanical linkages, not through a tendon, been able to get the finger to move. Now, it comes with some shortcomings because, again, they're not able to have direct control. There's coupling going on. They make a mechanism that will naturally come on down. And you can make a mechanism such that, one of them, you can engage it that it goes like that all the way down. So you get that curling motion that you don't want to have. The other is you can say it comes around here, and then at some point something engages and the rest of it will move on down there. And that means you're able to emulate what the human hand is able to do. And maybe it's good enough for all the tasks that you want, but it's still kind of limited. It won't be able to play the piano, won't have that kind of dexterity because no one figured out how to package that in there. So they're using the entire finger to be built up of these mechanical structures or linkages that are timed in such a way that they curl around. And some of them are pretty clever in that they even make sure that when they start to do the pip and the dip, that the rate of rotation there is the same as the range of motion. So as you'll see, my pip is able to go what I think is about 110 degrees or something like that. Whereas the dip down here, that one there is like maybe 80 degrees. So they have a different amount of rotation that goes on in there. So that can be emulated very easily with a linkage. But then again, what you're saying is that I've got a lot of coupling. I have 3 joints here, but only one actuator controlling it. What they've now done is said, wait a minute, rather than packaging linkages in there, let's just go ahead and package the motors there directly and figure out, because the natural way to align the motor is along the finger. The problem is the rotation has to come out that way. So that reducer that they have in there, I think is also key to it, so that they've got a compact motor and they've come up with a reducer that's able to come on out there. And that's why they have more strength than the other ones that we've seen out there. It's quite impressive.
I can just share a picture to kind of, let's see, share screen to kind of show how that is. So this is just to show that the thumb, if you're going for a tendon-based design or whatever, our thumb is pulled upon by 8 or in some cases 9 different muscles. Number 9 here is kind of like an extra interossei that sometimes is found also in the thumb. There are 9 muscles pulling in all different directions to create the motions of the thumb only. And then, as we said, if you can control the individual IP joints, when you strike or draw forwards, you could extend those joints. And when you're pulling back, you're using the long tendons here. Instead, you're just actuating the joints directly, I think would be really good. And yeah, this is the striking of the finger. And what I'm missing with this one, which I haven't, so Tesla is trying to do this, and we're coming back to the 5th metacarpal. We're doing it for the thumb. Can we do something similar for the little finger or the 5th finger? So when you to grasp something, the 5th metacarpal can be flexed, and it also rotates slightly on its own axis to get better into position for opposition with the thumb. So I think this muscle here is the opponent's digiti minimi, the opposing muscle of the little finger. So I think that would be really nice if they could get that. But as I said, you don't always have to emulate the human form. There are, of course, like looking at alternative shapes. We talked about this before. Is the human hand the best? So in the top 3 pictures and the one on the left, you have results of amputations or being born without the finger, and you have the Mickey Mouse in the middle. And then you have 3 kind of like made up hands would these be better perhaps? Would you have 2 thumbs, or figure 302 would be kind of like the 3-fingered hand of Boston Dynamics, for instance.
Boston Dynamics, yep.
Yeah.
But then there are also, and this is where someone might want to look away, but there are also people born with what's called a mirror hand, or a ulnar dimelia, I think it's called.
Cool.
And where you can this person lacks thumbs, so it's really hard for them to get a normal grip. But there are other options out there, so perhaps we don't have to stare directly at the human form.
Okay, that's a lot of food for thought. Fascinating.
Yeah.
I just got
I
inspired.
mean,
when
that's
preparing for today.
but now it just reminds me that anyone that comes up with a 4-finger hand, everyone's just going to call it a Mickey Mouse hand.
Yeah,
I know.
No matter how good it is, it's just going to.
No.
I mean,
That's what we call it to the patients as well. So usually, if you lose a finger and it becomes, sometimes it's painful, or if you lose the middle finger and it's like a gap between, you could do this removal of the whole ray. You remove the metacarpal and put it together, and then you end up with a Mickey Mouse hand. And if you don't look too carefully, you can hardly notice, because people move it so naturally. So if you lose one finger, not it can
There's so many conspiracy theories behind it as well, right? Why do most cartoon characters either have 3 or 4 digits in their hand?
It's easier to animate. This one I heard, but maybe there are others. No, it's
for everyone out there who was asking Scott and Gustav to break this hand down, you have been briefed.
And of course, hopefully, there are people at Wuji Tech that see this. They are more than
hopefully
invited. Yeah, they can come anytime. More than happy. Please come on here. And I have a feeling in a few weeks we might be able to get Tom Zhang of Doxo also come in here.
Yes,
so we'll look forward to that. Now he of course has the opposite approach. He goes with a lot of tendons, 108 at last count. And after looking at the thumb that you showed in the Kapandji, where there's like 8 or 9 tendons in there, it's got me thinking, it's like, wow, maybe Tom's onto something. Maybe that's the trick, is not having like the minimal amount, but the more you get in there, it kind of gives you a lot of that fine control. Because he certainly has control of a lot there with all of them. I definitely was able to see that when I was down there last week. So yeah, absolutely. We would love to have a representative from Wuji Tech on.
Yeah, definitely. And it's I have to say that we've been wondering about what's going on with the Chinese spots, right? And we're now beginning to see it. It's so exciting because you finally have a whole area. There's obviously competition will kind of breed a lot more ideas, and it's a fertile ground, and everybody learns from each other. So it's great to see these developments come out of China, and here's to many more. It will always give us more fodder for thought and to talk about and break down, so that we can keep these conversations going on over the horizon. All right, we'll have to leave it there for today. Thank you so much, gentlemen. Pleasure as always.
Thank you, Rock. See you later, Scissors.
Scissors always beats paper, right?
Always. Till next time.